Today, our central object of interest is time-dependent Schrodinger equation. So, we would like to solve for a molecular system this time-dependent Schrodinger equation in order to see the observables, let's say the eigenstates of the molecular system, which you can get by simply diagonalizing the Hamiltonian, which yesterday Nikolai talked about. They are just the part of the eigenstates. You still have other portions of the eigenstates, let's say electronic, vibrational, rotational. So one can see through time-dependent Schrodinger equation, you still get the spectrum, but not just as peaks, but as spread lines. And then the other observable, let's say population dynamics of different electronic states or vibrational states, one can see them. Yeah. All the dynamical phenomena that one expects to see of a molecular system can be obtained by solving time-dependent Schrodinger equation. Yeah. So let's write down this Holy equation. Yes. All of you probably are aware of this equation, right? Can you just tell me IH cross? Yeah, can. Yeah. So, yeah, you have a state vector from postulate 1 of quantum mechanics. You have a state vector describing the molecular system, which depends on time. And then it evolves according to time-dependent Schrodinger equation. This is a postulate, which means that it cannot be derived. So all of its predictions anyway are experimentally verified. So we take it as a postulate. You have the Hamiltonian of the system governing this time evolution of the state. Okay, so this is some abstract state of the molecular system which evolves in time, and all of the information about the system is contained in here. We need to solve this time-dependent Schrodinger equation in order to, this is the solution of this time-dependent Schrodinger equation. We need to solve. So it appears to be a very simple equation, right? Just first order in time, linear differential equation. But all the complicacy of solving this equation comes from the Hamiltonian sitting over there here. What does the Hamiltonian should contains? What does it contain? It has the kinetic energy and potential energy of the system, right? The information about the force fields within the molecular system. Depending on the molecular shape or the geometry, the potentials are complicated functions of these coordinates in general. Kinetic energy, one can approximate it up to second derivative, which we will see. So the whole of quantum dynamics has to deal with, one of the crucial tasks of the quantum dynamics is to deal with constructing the Hamiltonian of the given system. That means constructing the operator for the kinetic energy and the potential energy. And but before doing so, let's try to represent this this time-dependent Schrodinger equation here. Let's dress this with our familiar representation, coordinate representation. Yeah, how does it go then? Let's say, okay, so our interest is interest is molecular systems. So molecular systems, you just imagine for right now for the heuristic arguments that it's composed of, it's a soup of atoms and molecules, electrons, right? Nuclei and electrons. So in order to describe the positions of the nuclei and electrons, you need to associate them with their position coordinates, right? So in coordinate space, let's say I denote small r for the electrons and capital R for the nuclei. And then here, this becomes anyway a function of R and R. And I mean, in general, these positions are vector. I mean, these are vector. I just neglect the vector aspect because it doesn't concern us anyway for the main message. Uh, so how does it go? Yeah. So yeah. So what is this quantity called usually? So it's, I mean, our abstract vector is now dressed with this position in representation. So this is traditionally what we call wave function of a molecular system. Okay, this quantity. So the way it is denoted R T. Okay. Yeah. Yeah. No. It. Um, so I mean, we are we are representing the Hamiltonian in the position space. So it has the kinetic and potential energy. They are anyway functions of coordinate. These two coordinates. So that information is already in there. Yeah? Um, okay. So I just want to wipe it off. Oh, sorry. Okay. If I rewrite this. Sorry. So what's going on here? Then you have this. This is the total wave function for the molecular system, which is the function of the electronic nuclear coordinates governed by this time evolution. And this is the total molecular Hamiltonian. Yeah. So it's, I mean, now the total derivative has become partial derivatives because now it depends on R, and T, the wave function. Okay. So okay, now our goal is to solve this equation for molecular systems. TDSC for molecules. Okay, before solving this, let's identify the Hamiltonian for the molecule. Yesterday you were familiar with molecular Hamiltonian as yeah. Next page I can add. I see. How does it go? I'm just wondering. Uh, Next page. Okay. Insert. Okay. Yeah. Ah, okay. Then it's easy. Okay. Sorry. Okay, done. I'll try. Ah, you make. Okay, thank you. So it comes one after the other. After it. Ah, okay. Okay. So then I keep. Yeah. Okay. This Hamiltonian now is a function of electronic. Sorry. Okay. So this kinetic energy can now contain two parts, right? You have electrons moving in the molecule and nuclei vibrating in the molecule. So it can be composed of two portions. Now I take the coordinate dependence away just for the brevity. It's not matter. And then this vibrational energy, this potential energy can be due to the interactions between these entities. Let's say electronic interactions, which I write as VEE, electronic nuclear, and electronic nuclear. Yeah. This was the Hamiltonian written by Nico yesterday. So all of them, here this has the electronic coordinate dependence, nuclear coordinate dependence, and then electronic coordinate dependence, nuclear coordinate dependence. Okay. So given this Hamiltonian, we just want to plug it in the time dependent Schrodinger equation with an ansatz for the psi of r comma a guess wave function, because we need this is an initial value problem. We need to start with some initial ansatz to solve this problem, right? So what can be the you have the information about the Hamiltonian. What could be the possible ansatz one can guess? The initial ansatz one can guess for this. So now we understood that electrons and nuclei in molecules move on a different time scale, right? So which means the total Hamiltonian, which is the molecular Hamiltonian, it would be really glorious if we could separate electronic part and nuclear part, but we cannot do so here because there is Vn sitting there, which is dependent on both electronic and nuclear coordinates. But what one can do, we can write this molecular Hamiltonian, I denote with this molecular Hamiltonian as, let's say, the fast moving component direct product with the slow moving nuclear components. So that's what we can do, at least. Even if we cannot separate, the total Hamiltonian can be written as direct product of fast moving. It's a part due to fast moving electrons and slow moving nuclear part. Okay. So this is called adiabatic approximation. Yeah, fast and slow. Formally this is exact. There is no approximation so far. The total molecular Hamiltonian is given by the direct product of fast moving part and the slow moving part. If we now, let's say, assume that the frequency of the electronic states is much greater than the nuclear states, the vibrational states, which this means the electronic motion is much faster compared to the nuclear motion, because now we regard that nuclear part as a perturbation to the electronic part in the molecule. Like it's like electrons see the electrostatic field created by the nuclei on a time scale much slower than the frequency of the electronic states, yeah, the movement of the electronic state. Then we can regard this nuclear perturbation as a slow perturbation, and we are now in the adiabatic regime. Yeah. Yeah, these are, so it's like, so in the molecule you have electronic states and nuclear vibration levels, and this corresponds to the frequency between the nuclear vibration levels, yeah, and this is the frequency corresponding to electronic vibration. So you see the frequency are associated with the time scales of the motion, which are also indirectly proportional to the mass of the electron divided by the mass of the nuclei, yeah. So in that case, what we can do, we can, so in other words, electrons instantaneously adjust themselves as you move nuclei, yeah. So we can regard that the nuclear kinetic effect is minimal on the electronic movement, yeah. So which means we can set Tn to 0, we can fix the nuclear framework and let the electrons instantaneously see this electrostatic field and adjust themselves. Yeah, that's what this adiabatic approximation means. Uh, Still, we are not at the approximation. We are just, I mean, uh, there are cases when this is not going to be valid. Yeah, we will deal with that. But formally, everything is exact. We did not drop any term. Yeah, in this. Uh, so if then the H fast can be He electronic part, except for this nuclear kinetic energy term, except for this. So H fast can be I mean the spectrum of H fast can be given by the eigenfunctions of this particular Hamiltonian, if we regard that, if we keep the nuclear framework fixed. Yeah. Yeah, VNN. Yeah, I mean it's not removed. It's a constant. It has a non-zero value for a fixed nuclear framework. It has a constant value. Yeah. So you can just add it up. So I subsume everything in He electron except for kinetic energy of the nuclei, which is 0, because we are not allowing the nuclei the kinetic momentum to have effect on the electronic motion. That's the story at this level. Okay, so I mean only this particular I'm going to make you appreciate where this BO approximation comes from, where it breaks down, and afterwards I'll make a fast-paced presentation. Yeah. So in the limit of t n going to 0, yeah. So H fast becomes H electronic. So then H electronic, if you could solve, I mean this has the both nuclear electronic dependence, but now since we are fixing the nuclei, since Vn of Vn, this electron nuclear potential and electronic, it's the only this one, and Vnn contain the nuclear coordinate dependence in this particular portion of the Hamiltonian. We parameterize this Hamiltonian with respect to this R, capital R. Okay. So in that case, just yeah, we can write that. Yeah. Let's call the electronic portion as okay. So this, if we could solve for this, keeping the nuclear framework fixed, we get the fast moving electronic wave function for the molecules. So this is what is the job of quantum chemistry packages. Yeah? So they provide you for a given nuclear distance, they provide you the energy points, and then if you scan along R, you get a set of points for each electronic state, and then keeping the order, if you can connect them, you get adiabatic potential energy surfaces, because this is adiabatic because of omega L much greater than omega nuclear, and we are setting Tn equal to 0. Okay. So something like this. Suppose if you do the electronic structure calculation for, let's say, some molecule, you get the energies as points at this R, and some other R you may get this set of energy levels, And if you keep this order and connect these points, you get so-called adiabatic potential energy surfaces. Yeah. In multi-dimension, for one-dimensional system, they are just curves. For multi-dimensional potential energy surfaces. Okay. Yeah. Yeah. It's adiabatic because we are. Yeah. Okay. In classical I mean, it's not the classical thermodynamic sense we call it adiabatic. It's like you have a perturbation which is very slow that allows your internal degrees of freedom to adjust sufficiently rapidly to this perturbation. That means they have enough time to adjust to this perturbation. So if that's the case, we call it adiabatic. So if there is an external perturbation which is slow, I mean whose frequency is uh, much lesser than the frequency of the internal energy spectrum, then you could call it adiabatic in that sense. So it's like now you have a nuclear electrostatic field created by the nuclei inside the molecule. Electrons feel this, but instantaneously. So this is a perturbation for the electrons, but electrons, nuclei did not even notice that, but the electrons have adjusted to it. Yeah. So in that sense, the nuclear perturbation is quite slow compared to the electronic readjustment, I would say. Yes, absolutely yes. Absolutely yes. Yeah. Completely? No, it's not zero. Since if we are fixing it, yeah, we are fixing the nuclear framework because it doesn't matter for the electrons. They don't feel the nuclear. I mean, they don't feel the nuclear moment. Yeah. In the sense, no. The nuclei do not feel the electronic movement. Yeah. So for electrons, it's like nuclei are fixed. That's how it goes. Yeah. So that means when you fix that, there is no momentum for the nuclei with respect to the electrons. Yeah. Okay.